Hey, everybody. John Mason here. Today, for this little laboratory, this is lab 5, I think, measuring the magnetic field of the Earth. And what we're going to do is we've got to set up with some Helmholtz coils so we can make our own magnetic field. And I have a little compass needle here setting so that the compass needle, when there's no current in the Helmholtz coil and I'm making no synthetic magnetic fields, the compass needle is pointing just completely parallel with the plane of the two hoops here in the laboratory. So in other words, this compass needle points along with the direction of the magnetic field of the Earth. Let me show you from a top point of view. So here you see the Helmholtz coils and you see the compass needle pointing just completely parallel with the plane of the Helmholtz coils. Okay. Now, what I'll do is we are going to make a sequence of measurements where we turn on, using our friend the lab volt here, we turn on the current, which makes our own magnetic field, which deflects the needle. So you can see the needle here. Now watch as I turn this on just a little bit. So. Okay. So this isn't the best perspective to see the needle, but you saw the needle move. Here we have 10 milliamps. All right. And when we go over here, we see that the needle has now deflected by some amount. And if I stop this needle from deflecting, we can come over here and make our first measurement. So it's going from about 270 to I'm going to say 254, about 254 if we let it settle down. So that's 24 degrees of deflection with a 9.8 milliamp. The dimensions of this are that this thing, the Helmholtz coil dimensions are kind of similar to what we've had previously. It's that the Z is 7 centimeters and the R is 14 centimeters. These are the dimensions of the, did I write that? Z is 7 centimeters, R is 14 centimeters for the dimensions of the Helmholtz coil. So what you can do is you can use the Helmholtz coil equation for the B field to calculate, given a 9.8 milliamp current. Oh, and the fact that this thing, the number of coils is 134. Okay, so the coil's wrapped around 134 times. So whatever you do when you calculate the B field of the Helmholtz coil, you're going to have to multiply by 134 since there's 134 times of this 9.8 milliamp current. Okay. Now what I'll do, so our first measurement basically consists of the current measurement and the 24 degree deflection angle. Okay. Now next, I'll turn it up a little bit. Now I'm going to go to 13.8 milliamps. All right. And I'll stop the little needle from rocking too much. And we find ourselves at about 220, 249. Sorry, not 249. Going from 270, so there's 10, 20, 30. I want to say 38 degrees of deflection. But I'm going to call it 38 degrees of deflection, counting the degrees of deflection from 270. And that's our second measurement. Next, I'll turn it up a little more. So now we're going to go to 26.8 milliamps. And I will stop this little needle from rocking the best I can. And let's come over and make a measurement here. If I look at this, I suppose from 270 it looks like from 270 all the way to 220 and almost to 230. Sorry, almost to 210. Maybe 215. So that's 10, 20, 30, 40, 50, 56 degrees. I'm going to call that one 56 degrees. Okay. And then one more measurement. I'll crank up the current even higher. We'll go to 38 milliamps. Now let's go a little higher than that. Let's go to 51.5 milliamps. And I find my deflection 10, 20, 30, 40, 50, 60, 75. I'm finding about 75 degrees of deflection, which you can verify for yourself there. 10, 20, 30, 40, 50, 60, 70, maybe 73. I'm going to go with 73. Okay, at 51.7 milliamps. And those are our raw data for the charge to mass ratio, sorry, for the magnetic field of the Earth. So just to show you on the lab report here, you have these, I've just kind of measured the current in milliamps and the deflection angle. So you can convert the current to amps. The deflection angle will be in degrees. And then you can use the Helmholtz coil equation to convert the current into B field. And you can use a little vector geometry to show that the horizontal B field of the Earth can be gotten, because what's going on here, if I sort of write on the board, I guess, here, what you've got is at the point P in the middle of the, see if I can draw here. Good, okay. So at the point P, right in the middle of the Helmholtz coil, if I imagine looking from top down, the B field horizontal of the Earth points just along the direction of the Helmholtz coils. If the Helmholtz coils are kind of like this, okay, but the Helmholtz coils themselves are making a B field that points kind of completely perpendicular. And so the actual total compass needle is deflected by an angle beta that's here. And so what you see is the tangent, oh, sorry, I should write down here. But tangent of beta is basically opposite the B field that you know over the B field horizontal of the Earth. That's the Earth, the one that we don't know. And it turns out that since we measured beta and we can calculate the B field from the Helmholtz coil, we can figure out that the B field of the Earth horizontal is equal to the B field that we calculated divided by tangent beta. So you can calculate 4 different versions of this and compare to the 22 microteslas that the Colorado horizontal component of the B field is. All right. Okay, so that's part 1 of the lab. Part 2 is actually really quick, because then what we're going to do is realize that the magnetic field is not just a totally horizontal thing. We just measured the horizontal component because compasses, when they point in certain directions, are always constrained to just point in the horizontal plane. So they don't necessarily pick up the vertical direction unless you've got a compass that really points in 3D. So let's show you how this looks. Okay, so now I have my compass here free from any synthetic magnetic fields. And I'm going to line it up so that basically this arm of the compass, which can rotate freely like this, is lined up with the compass needle. And so so since the compass is free to basically rotate in this kind of this way, there's absolutely no component to the B field pointing perpendicular like my finger points, okay? So all the B field is in the plane, kind of the vertical plane that we have by looking down on this situation. So what I'll do is now, if I turn this vertically, the compass needle will dip below horizontal by some amount, and that's known as the dip angle. So you can come over here and you can see how much below vertical the compass needle is dipped. And so since 90 is the completely horizontal, and we're kind of oscillating about 30, that's about 60 degrees. Okay, so that's about a 60-degree dip angle. Now, doing a little similar geometry that I did over here on the board, I can do some analogous geometry with the vertical component here. And we can calculate the B field, the full B field of the Earth. So now we're going to use our known horizontal B field. So we have our horizontal B field like this, but we've got the full B field of the Earth like this, and it's just dipped some angle alpha. And so cosine of alpha is adjacent over hypotenuse, or BH over BE. So I can calculate the full B field of the Earth knowing the horizontal component in the dip angle, which is 60 degrees. So BE is horizontal component that we just calculated over cosine of alpha. Okay. And so that's how you can calculate the full magnitude of the B field of the Earth. And you can see that the B field is not, that compass needle is now pointing in the direction of the magnetic field of the Earth. And you see it's not horizontal. In fact, the B field of the Earth points directly, almost more directly into the ground than it is even horizontal. So hopefully that's enough to get you through the lab. And thanks, everybody.